All right. I thought I would start today by proving Fermat's last theorem. So let's prove Fermat's last theorem. So does anyone know what Fermat's last theorem is? What the statement is? Who is Fermat? Anything about this? Stephanie.
Yeah, was it if you have x cubed plus y cubed equals z cubed, there are no integral solutions?
If x cubed plus y cubed
Or
equals
it
z
was-
cubed,
If
no,
n is greater than 2,
and n is strictly greater than 2,
then there are
then
no integral solutions.
no dyslexic
Non-trivial.
integer, non-trivial integer solutions. In other words, maybe, so if x to the n plus y to the n equals z to the n with n greater than 2, so in particular we're avoiding the Pythagorean theorem where x squared plus y squared equals z squared. There are, like 3, 4, 5 is a solution to x squared plus y squared equals z squared. So what's a trivial solution?
0, 0, 0.
You're not allowed to answer. This is for 0, 0, 0 is a trivial solution. Tell me your name again. Karen. Right. Karen. 0, 0, 0 is a trivial solution. Any other trivial solutions? Other than Karen? 1, 1, 1. 1 to the n plus 1 to the n is 2, which is not 1 to the n. 1, 1, 1 would be a good solution, except it doesn't solve the equation. There are other solutions that we should be able to eyeball, like 1, 1, 1 and 0, 0, 0. What is it? Tell me your name again. Xiang. And Sheikh. Right. 1 to the n plus 0 to the n equals 1 to the n. Also, 0 to the n plus 1 to the n is 1 to the n. Right? So there are a bunch of these. Also, let's say n is 24, then negative 1 to the 24 plus 0 to the 24 is negative 1 to the 24. Right? So lots of trivial solutions. 0, 0, 0 is a trivial solution. 1, 0, 1 and 0, 1, 0 is a trivial solution. If n is even, then negative 1, 0, 1 or negative 1 is also a trivial solution. Any others? Daniel?
If n is odd, then negative 1, 1, 0 would be a solution.
Negative 1, 1, 0. Love it. So if n is odd, then negative 1, 1, 0. Because that's negative 1 plus 1 equals 0. What else? Yes? Don't tell me. John.
Yeah. M, 0, N.
Yes, very good. We also have M, 0, M. Mom. 1, 0, 1 is a solution, so is M, 0, M. Mom. Okay? M to the n plus 0 is n to the n. Is there okay, any others? Don't tell me. Karen?
Didn't just like any of these multiply by n?
Yes, all of these can be multiplied by m. In fact, so this equation, there's something interesting about this equation. This equation is, there's a word for what this equation is. I don't know if you've heard this word. If if you have a polynomial where all of the monomials have the same degree, that has a name.
Is it Diophantine?
Diophantine, okay, so this is an example of a Diophantine problem. Diophantine is polynomial equations that you're trying to solve in integers or rationals. So that's a great, let's put that on there. So this is a Diophantine problem. Diophantine, problem. So Diophantine problem means polynomial equations, generally, polynomial equations solved in integers or rational numbers. Now, when this happens, and you can't see, what should you do? Can everyone, whenever this starts happening, give me a thumbs up so that I know I'm looking at you. I don't see what's happening here. So if that starts to happen, you give me a thumbs up, and I know to slide it up. Okay? Deal? So it's a Diophantine problem because it is a polynomial that we are trying to solve in the integers. It's no problem finding real number solutions to this, right? 1 to the n plus 1 to the n, that'll be 2, and I take the 13th root of 2, and that's z. And that solves x to the 13 plus y to the 13 equals z to the 13. No problem. Real roots, not an issue. It's integer roots or rational roots. Now, if we have a rational root, do we necessarily have an integer root? Maybe 7/3 to the 13 plus 5/11 to the 13 is equal to some rational number to the 13. Could that happen? So if that happens, this is right back to why mom is a solution and the word I'm looking for. So I'll give you the word. The word that I'm looking for is homogeneous. This polynomial is homogeneous. So it's a funny word. So homo means same. Genus is in this case what genus is referring to. Genus is one of those words that mathematicians love. Genus is like species, file of class, order. Genus is like what kind is it? But of course, mathematicians classify a million things into kinds. So it's a horribly over-abused word. In this context, genus means the degree. So they all have the same degree. X to the 13 plus y to the 13 equals z to the 13. All of the monomials, all of the pieces in the polynomial have degree 13. When that happens, there becomes a relationship between rational solutions and integer solutions, precisely for the same reason that mom is always a solution. If 1, 0, 1 is a solution, so is m, 0, m. You can scale. If you multiply all the variables at once by any constant, it'll still solve the equation because that constant to the 13th power plus the same constant to the 13th power just pulls out. Does that make sense? Let me write that down. So what this means, so if there exists, if I use a symbol, like a mathematical symbol, that you don't understand, and you still don't understand it after I write it and say it out loud, please put your hand up in the air if you don't understand a single thing I'm saying, that it's not your fault, it's my fault, and I guarantee you there are 15 other people in the room who don't understand it either. Okay? If you don't understand something, don't let me go on. Hand in the air, I don't get it, and you're helping not just yourself, but 10 other people, 20 other people, promise. Okay? So if there exists a rational solution, in other words, x, y, z in the rationals, this means rationals. Everybody has seen this symbol for rationals? This is the symbol for integers. Bold z, bold q. Okay? So if there exists a triplet of the rationals satisfying star is, you can still see it, star is this equation, so the equal sign is what I'll put the star on. If there exists a rational solution to that equation, Yes, thank you. That's what I was looking for. Some thumbs up, because you can't see. So if there exists a rational solution, because it's homogeneous, because the degree of all the polynomials is the same, just multiply through by the denominators. So in other words, so if there exists a rational solution, like pretend, I don't know, 7/13 to the 24 plus 9/11 to the 24 is equal to whatever, 5/3 to the 24, right? Let's pretend that's true. Let's pretend we had a rational solution to the equation with n equals 24. Well, then what could I do? Behind Karen, what's your name?
Jinghua.
Jinghua.
I was wondering why is 0, 1, 0 different instead of 4?
Why is 0, 1, 0? Oh, sorry. 0, 1, 1. Very good. Thank you. Did everybody else see that 0, 1, 0 and you knew I meant 0, 1, 1, but you let me get away with it anyway? I hope the rest of you saw that that wasn't the solution. I probably said out loud 0, 1, 1, but wrote 0, 1, 0. Don't let me get away with that, okay? Stop me right away, because for the last 5 minutes while we were talking about this, you've been thinking, he's got it wrong, I should correct him. He's got it wrong, I should correct him. A part of your brain is working on that problem instead of working on these problems, okay? So don't, if I write something and you know it's wrong, help yourself and me and others by immediately objecting. Other than Karen, can someone tell me what you would do if you found this, if this equation pretend was true? Andrew. No, Alex.
Close. Just multiply by the denominator.
Multiply through by 13 to the 24th times 11 to the 24th times 3 to the 24th. And because it's homogeneous, we can do that, and that will give us an equation. So if there existed a rational solution like this, pretend, this is not true, but we're pretending it is, then multiply xyz, multiply by denominators, in other words, if this is your xyz, then what is it? 13 times 3 times 11 x, comma, 13 times 3 times 11 y, comma, 13 times 3 times 11 z. All the thumbs are going up, thank you. Then that would be an integer solution. And it would still be a solution because when you multiply through all three of these, you haven't changed these factors all just pull out of everything. Does that make sense? Question?
When those constants be to the end.
So those constants, this is what I mean by an integer point.
Okay, never mind.
And then when we put them in, they get raised to the end. Exactly. When you put them into the equation to test if it's true, assuming the original equation was true, the new equation is still true, but now you have an integer solution. So having a rational solution is equivalent to having an integer solution for a homogeneous equation. This is actually called projective, but never mind. That's why projective geometry is useful in number theory. You would think, what is geometry doing in number theory? It's there, and it's there in spades. Okay. So so how can we classify non-trivial? So how can we classify the trivial solutions? Let's go back to the trivial solutions for a second. So we found a whole bunch of trivial solutions, even correct ones. Is there anything that they all have in common? Okay, some hands going up. Alex sees something, Karen sees something. William, was your hand on the way up?
Yeah, I mean, they all involve 0.
Yes! They all involve 0. Check out what happens when one of these is 0. Then you just get x to the n equals z to the n. Sure, million solutions to that. Or z equals 0, well then you have x to the n equals negative y to the n. Plenty of solutions to that if n is odd immediately. They all involve a 0 somewhere. So how can we, so how can we state Fermat's last theorem in a really slick way using the fact that one of the terms, I don't know which one, has to be 0? How could we package this logically into one statement? How can we capture the condition that at least one of the either x or y or z has to be 0? Well, we just say either x or y or z has to be 0. William?
So the condition of n is greater than 2, you would just also include x union y union z can't be 0?
Yeah.
That's the key.
So here's a slick way of stating Fermat's last theorem so that you don't have to write the word non-trivial. You say if, this is what I was starting to say, if x to the n plus y to the n equals z to the n, and n is greater than 2, and of course I mean and x, y, and z are integers, and n is an integer, then, Alex?
Can you say that none of them are the same? So x doesn't equal z, x doesn't equal y.
Okay, that's a good guess. They can't all be the same, but actually 0 and 1 aren't the same.
Well, just none of them could be the same as the.
How about negative 1, 1, 0? They're all different. Good guess, Karen?
X, Y, Z, Y, 0.
Yes, the product. That's what I was hoping to see. So if x to the n plus y to the n equals z to the n, and n is greater than 2, then x times y times z equals 0.
Not even.
If you have a solution, then you have a trivial solution. That's the other way of, that's the contrapositive of saying there are no non-trivial solutions, means if you have a solution, then it's trivial. Does that make sense? So this is the one-line version of Fermat's last theorem without going into all this discussion about trivial solutions, homogeneous solutions, what they all look like. So if x to the n plus y to the n equals z to the n, and n is any exponent greater than 2, then x, y, z equals 0. In other words, we have a trivial solution. The only solutions to this equation are the trivial ones. Now this seems like a silly problem. Who cares? Why this? Anybody know why this? What is this theorem? Knowing this theorem, what does it prove about the world? Your blank stares are correct. It proves nothing about the world. This theorem is an example. This is my interpretation. This theorem is an example of something that's like the peak of a mountain, or the moon. We put a man on the moon. Now what? What have we learned? Well, we learned something about the moon, actually. We brought back some moon rocks, and they were really cool. It's the act of going there that created a million different technologies that maybe we wouldn't have had otherwise. It's the act of proving this last theorem, which, does anyone know who proved Fermat's last theorem? John?
Wasn't it Andrew Wiles?
Andrew Wiles, that's right. Just 30 miles from here, down in Princeton. There's a long and beautiful story, and maybe one of these days, it probably won't take class time to do it, but you should definitely watch. There's a beautiful Nova special on the proof of Fermat's last theorem, which goes through a partial proof of the Taniyama-Shimura conjecture involving Gauss representations, and uses Jacquet-Langlands and Jerry Tunnel, who's in our department here, Tunnel-Langlands. Just the amount of machinery that went into climbing this mountain so that you could say, yay, we climbed the mountain, is what makes this mountain worth climbing. So let's prove in the next 30 minutes this theorem for a special case, which actually Fermat himself did do. So the story of this is that, so Fermat's last theorem, Fermat, right, I should really call this Wiles. This is Wiles, Andrew Wiles, and Taylor Wiles. So Richard Taylor, who was at Harvard at the time, but then moved to the Institute for Advanced Study in Princeton, and now has moved again to Stanford just recently, was Andrew Wiles' student. And the famous story is that in '93, Wiles announced the proof, and then as people were arguing, as people were studying his proof, they discovered a flaw. They discovered something, they kept arguing with him and saying, no, I don't understand, and then they realized there was an actual problem in the argument. And that was in '93, immediately after he announced the proof. there's a whole other controversy, maybe you care, maybe you don't care, which was that he was turning 40 shortly after 94, and 94 was when there was an ICM, the National Congress of Mathematicians, which is where the Fields Medals are handed out, which you have to get before you're 40 years old. So finally in 94, his major manuscript is Wiles, and then an additional manuscript that fixes this flaw is by Taylor Wiles that finally finishes the proof of Fermat's last theorem, which anyway is based, I should write 100 different names for the eventual proof of this. Sophie Germain and Serre and Ribbit and a million other people. But in 94, he eventually gave the proof that now that fixes the gap, but it was too late for the ICM, and he wasn't given a Fields Medal, and it was, there was this huge. Anyway, it's a long story. We can talk about it some other time. In the interest of time, let's prove Fermat's last theorem. In the proof, so Fermat stated this in roughly in the 1650s. Taylor Wiles is 94. Published in 95 in the Annals of Mathematics. But Fermat, so what's the story with this last theorem? Does anybody know? Why is it called his last theorem? Why is it called his theorem first? Sheik?
Because he died after that.
He did die, that's true. He died without, so he was reading Diophantus's geometry. Diophantus is an ancient Greek from like 300 Common Era, 300 AD, who was, sorry?
No, sorry.
Oh, please. It was about this or about other stuff?
It was
Okay, sorry. So he was reading Diophantus's geometry. He saw the statement of the Pythagorean theorem and Diophantus's study of the solutions to the Pythagorean theorem. In other words, when n is equal to 2, there are lots of solutions, as we already discussed. And he wrote in the margin to Diophantus's geometry, he would write all kinds of fascinating discoveries that he made that nobody had made previously. After he died, this book was sent to a bunch of mathematicians who started going through his claims, and they, one by one, started providing actual proofs. Because sometimes he would give a Sketchman argument, sometimes he would give a full argument, and sometimes, like in this case, he would say, the proof is too complicated to put in the margin. And that's how he left it. He says, I've discovered this marvelous fact that x to the n plus y to the n is never equal to z to the n, has no non-trivial solutions for n greater than 2, but my proof doesn't fit in the margin. We don't know what his proof is. No one today, no one seriously believes that he had a complete proof. But there's one case where he, in a separate letter, provided enough arguments that we know he really did have a proof when n is equal to 4. So that's what I want to do. That we can do if I shut up and get to math. That we can do today. Okay, so let's prove Fermat's last theorem for n equals 4. Ready? Any questions? So far, so good? We got the T ready. We got pens and sharpened. Let's do it. So Fermat's last theorem. So this is Fermat's last theorem. So the last is that it was the last of his claims to remain unsolved. Everything else was either demonstrated to be true, or he got a bunch of things wrong. So we didn't know if, so Fermat's last theorem, 4n equals 4. Okay, so if x to the 4 plus y to the 4 equals z to the 4, then x, y, z is equal to 0. There are no non-trivial solutions. Right. In order to solve this, in order to prove this theorem, we need to go all the way back to what Diophantus had actually done, which was to understand solutions to the Pythagorean equation. So let's do that. A first step. It's still showing through, that's okay. I'll get clearer paper next time. There's something I want to do with this. So first step is, what do we know about solutions to the Pythagorean equation? Pythagorean theorem. Right? We're talking about right triangles with side lengths x, y, and hypotenuse z. So, you guys know the Pythagorean theorem? Yes. You know they're integer solutions to the Pythagorean theorem. 3 squared is 9, 4 squared is 16, 9 and 16 is 25, which is 5 squared. Right? So, here's the theorem. Ancient. This is actually what I hope to show you in a second. If x squared plus y squared equals z squared, and let's have some conditions here that I want to discuss. So, is this equation homogeneous? What's the degree of this monomial? What's the degree of this monomial? Okay, so all the monomials have degree 2, so it is a homogeneous equation. We can think about rational solutions, or we can think about integer solutions. We can also, if they all have a factor in common, we can pull that factor out, right? If x, y, z is a solution, then so is 7x, 7y, 7z, because the 7 squareds go everywhere and give you a new solution. So what we want is a primitive solution, and primitive, i.e., there does not exist an integer d dividing x and dividing y and dividing z. In other words, if x is a multiple of 7 and y is a multiple of 7 and z is a multiple of 7, just divide all of them by 7 and get to a solution that doesn't have 7 as a divisor. And 2 and 3 and 13 and 24 and whatever. Okay? Get rid of any factor that all of them have in common, divide that out. Right? So that'll be a primitive solution. So if x squared plus y squared plus z, equals z squared and is primitive means this. Does that make sense? So 3, 4, 5 is a solution. So is 6, 8, 10. So is 3 times 3 is 9, 4 times 3 is 12, 5 times 3 is 15. 9, 12, 15 is a solution. Don't worry about those. Divide out that common factor and get to a primitive solution. 3, 4, 5. They have nothing in common. So the theorem that I want to prove is if x squared plus y squared equals z squared and there's no factor in common, then z is odd. One of these is odd. We may as well assume that x is odd and y is even. Then z is odd. We can choose now one of these to be odd. It's the sum of two things is odd, then one of them is odd and the other one is even, and assume x is odd and y is even. I'm not getting thumbs up. Give me the thumbs up so that I know, okay? So that I know I need to slide this up, not too far. So if this is a solution and it's primitive, then this happens. And moreover, and there exist integers Rs, one even, one odd, and coprime, one even, one odd. I don't know which one is which, doesn't matter. So that x is r squared minus s squared, y is 2rs, and z is r squared plus s squared. This is the magic formula. Let's test this out. Let's try to unpack this theorem. So here's a triple. Let's see if I can get this right. Here's a triple. 10, 24, and 26. Oh boy. So I claim that's a Pythagorean triple. 10 squared is 100. 10 squared is 100. That's easy. 24 squared. 20 squared is 400. 4 squared is 16. We got 416, but then we need 4 times 20 is 80. Times 2 is 160. 400 and 160 and 16. 576. Did I get that right? 576. I'm not testing your mental arithmetic. Do this with a calculator. And what about 26 squared?
676.
676. It's a good guess, and it's actually right.
Just gotta add 100.
Because you gotta add 100. Okay? So this is indeed, the sum of these two is that. So it's a Pythagorean triple. Everybody see that? This 10 squared plus 24 squared is 26 squared. Is it primitive? No, not primitive, so the theorem can't apply. Z is not odd. There's a factor in common for all of them. What's the factor in common for all of them? 2. So a primitive solution, so if we divide by 2, so this is not primitive. So divide by 2, that leads to 5, 12, 13. 12 squared is 144, 13 squared is 169. 144 plus 25 is 169. Okay, so this is, now is this primitive? Yes. Is Z, so this is primitive. 25 plus 144 is 169. And yes, primitive. Let's try this one. Yes, this is primitive. Don't want to lose. Okay, so my assumption is that x is odd and y is even. Is that correct, Karen?
Is it necessary to assign odd or even to one x or one y in order to like create the premise of the proof, or can you assume x is odd and y is even when you start proving it? If that makes sense.
So there's a symmetry in x and y. All I'm saying is one of them is odd and one of them is even. I don't know which. But if you look at the parametrization that we're giving, we're going to find some r and s that makes this equation true. And look at y. I'm forcing y to be the even one. Okay? So that's why I have to say which one is which. If x was the even one, just switch these two. They're completely symmetric. Are we in position here? Do we have 12, 5, 13 or 5, 12, 13? Which way do we want it? This way is good, right? Because these two are odd. So z is odd and the 5 is odd. I'll try to write a little bigger. Okay, so we're in position to apply this theorem. There needs to be, the theorem says, there must be numbers r and s, so that 5 is a difference of the squares in r and s. 12 is twice r and s. In other words, r times s is 6. And 13 is a sum of r squared and s squared. So what are r and s in this case? You got one? Tell me your name again. Devendra.
Yeah, r is 3 and s is 2.
Okay, so Devendra says try r equals 3 and s equals 2. So if r is 3 and s is 2, okay, so 3 squared is, so I'm putting in this formula. 3 squared minus 2 squared. 9 minus 4?
5.
5. That's x. Check. How about 2rs? 2 times r times s. 12. That's y. That checks out. And 13, r squared plus s squared. 9 plus 4. Thumbs up. 9 plus 4. 13. Okay? And r and s are co-prime. They have no factors in common, and one of them is even. And one of them is odd. Okay?
Does r and s have to be unique or not?
So, do they have to be unique? Excellent question. Do they have to be unique? So let's stare at that. equation. Does anybody have any ideas? Alex?
Can you just scale with a constant?
Okay, if I scale R and S with a constant, first of all, they no longer are co-prime if I scale them with a constant. Second of all, if I scale them with a constant, I have to scale X and Y by the square of that constant. Question? Hand up? No? There is one thing you can do to R and S, precisely because we've parametrized X, Y, and Z. You know what I mean by parametrized? X, Y, and Z are now functions of something simpler, R and S. In terms of homogeneous quadratic polynomials in R and S. And there's something you can always do to homogeneous quadratic polynomials. Multiply both R and S by... You're not allowed! Come on, Andre. Yes, -1. So if you multiply R and S by -1, let's look at this equation. If I put here -3 and -2, well, when you square negatives, you don't get anything. Multiplying both of them by negative sign doesn't change this, and again, squaring doesn't change. Okay, so they are unique up to. So if you insist that both are positive, then it's unique. I'm sort of I'm hand waving a little bit between positive solutions and integer solutions. I am kind of thinking in my mind about positive solutions. At least historically, that's what people were thinking about. Although the modern point of view is that you shouldn't be thinking about positive solutions, you should be thinking about all solutions. Question?
What does it say before R equals 3?
Try. This is try. And I will try to write better. Okay? So, if I gave you now, Dipendra? Dipendro. How did you find that RNS? You just kind of guessed.
Well, I just told you I read through about 6 and then just found
Great. You took 12 divided by 2, and you saw that it was 6, and you thought about what the divisors of 6 could be and what could their sums and differences of their squares be. Beautiful. That's actually how the proof of the theorem goes, believe it or not. Sort of. If I gave you a giant number, a giant triple, guessing and checking would not be a great way of doing it. So that's the beauty of proof. We'll prove the theorem, we'll prove that you can always find such a thing. Now, before we do that, let me give you an exercise. So I promised I would give exercises in class. The exercise is the converse theorem. Now the converse theorem doesn't need any conditions, nothing about being integer valued or coprime. If for any two numbers, real, complex, p-adic, whatever, we're going to get to p-adic numbers, by the way. That's something we're going to cover. You don't have to know what that means yet. For any numbers R and S, if you set x to be r squared minus s squared, y to be 2rs, and z to be r squared plus s squared, then the triple xyz will satisfy that equation, x squared plus y squared equals z squared. Just algebra. Okay, so this is exercise 1 is the other direction. If x is r squared minus s squared, y is 2rs, and z is r squared plus s squared, then x squared plus y squared equals z squared. No conditions, no restrictions, nothing. All right, let's prove this theorem. Yeah, okay, we're not going to get to Fermat today. Actually, since I have this here today, we're going to prove the theorem tomorrow. I want to show you something. I want to show you how old this idea is. I said ancient. I want to quantify that ancient. So let me pass this around. Okay, everybody grab one of these. Let's get some piles going around. I will show you one here. Zooms out. In fact, I can zoom out quite a bit and still it'll still be visible. Anybody have any idea what the hell we're looking at?
A manuscript?
Good guess. Manuscript's a good guess. It's certainly, so I guess I always think a manuscript is being written on parchment or something. This is a little little clay tablet.
Yeah.
It's the size of your palm. Does everybody have theirs? Anybody not have a copy? Okay, a couple in the back didn't get yet. Are we running out of copies? I have one here. Who else needs? A couple more back here. What is it? Plimpton. Plimpton. This is called Plimpton 322. So this is an ancient Babylonian tablet. This is Babylonian tablet. Babylonian tablet. It's been dated to roughly the year 1800. The year 1800 BC. So if you want to think about what that means, you remember the ancient Greeks like Euclid and stuff like that? Euclid predates us by about as much as this predates Euclid. Okay, it's 2,000 years. You have to go back 2,000 years to get to Euclid. From Euclid, you have to go back almost 2,000 years to get to this. Okay, to give you some sense of scale. Now, what's on here? Well, there's something you have to know about ancient Babylonian writing techniques. This document sat in warehouses for a long time until people figured out what was on here. So the first hint is this first column. The first column, this is a slash, this is 2 slashes, this is 3 slashes. Then you get 3 slashes and a 4th slash. Can you kind of see that? Then there's a bunch of stuff missing. It's hard to see here. The first time something interesting happens is here. Instead of slashes, you get this thing. And let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this thing equals 10. This thing means 10. All right? Let's work on this 7th line. This is line 7. So this is 1, 2, 3, 4, 5, 6. This is kind of the first one that we can really see what's going on. This is line 7. So 7, so they would write, it sort of looks like, so look at 9. 9 is a full, their utensil, it didn't really make, it made a thing that looks like that. That would be kind of 1, 2, 3. Then you would see 4, 5, 6. And then you would see this marker is too heavy. 7, 8, 9. So this is 9. This is 9. So you can get up to 9 using marks like this, and then when you need to do 10, you do a diagonal mark, a sideways mark. And then this is 11. It's a 10 and a 1. And 12 is a 10 and a 2. And what you'll see is you'll see up to 5 10s. So you can make 5 10s and 9 1s, which means you can get from 0 to 59. So these ancient peoples were using sexagesimal numerals, which means base 60. Weird, right? Who uses base 60? Anybody have the time? Oh, time is in base 60. How many inches in a foot? 12. Where does that 12 come from? Base 60. 12 is, you can count 12 on your fingers. I'll do it here. I'll just do it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you do that 5 times, you get to 60. So 60, there are roughly 360 days in a year. So they considered the angles around a vertex to be 360, because that represented a cycle. And if you take triangles, you can take 6 triangles, 6 equilateral triangles, and fit them around a vertex to fill out that vertex. So each equilateral triangle got a 1/6 of the 360 degrees. So an equilateral triangle has 60 degrees in each in each angle. Okay? That's where this all comes from. These quote-unquote primitive ancient people, Babylonians. This is modern-day Iraq. You're going to see, at level 7, you're going to see a ginormous Pythagorean triple. Absolutely astonishingly large for guess and check. If they really had no technique for finding Pythagorean triples, there'd be no reason for them to be able to find this one. They had a technique, and the technique that they had was exactly this theorem. They understood this parametrization of Pythagorean triples, which meant that they could create arbitrarily large Pythagorean triples, including the ones that we'll see here. Okay? If this doesn't completely blow your mind, well, then you've seen it before, or you have no heart. Okay, so let's go through line 7. So let's look first at this thing here. Does everybody see what this is? Let's try to make sense of this. So let's see. I don't know what to call this. Let's call this line 7. Line 7. Can I say column -3? Does that make sense? This is column -1, -2, -3. I mean, we would number. Okay, let's do it forwards. 1, 2, 3. Column 3. So either way, plus or minus, it's column 3. Column 3. It's hard to see, so let me make sure I'm deciphering it correctly. I did it at home and checked against what I'm supposed to find. Right. What I see here is correct. Yes, good. Okay, so what I see here is 1, 2, 3, 4, 5. I think that's roughly what the tens place is. And the ones place, I'm seeing 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a little hard to tell. You have to go with it. But that roughly looks like 5. That roughly looks like 9. That number is 59. And then next to the 59 is looks like a 1. Just a big 1. Does everybody see that here? This is 59, and that is a big 1. So what does that mean? 59, let me separate them by a comma. This is one of the things they were missing, by the way. In the sexagesimal system, people who don't appreciate the number 0 from ancient India are missing out on the fact that there's the sense of place value is fluid here, and you have to use your intuition to figure out what place value actually means. That's one of the difficulties in deciphering this thing. But let's take this as our assumption. What does 59, 1 mean? If we're in sexagesimal, it means 59, so this means 59 times 60 plus 1 times 60 to the 0. Just like what does 59 mean? It means 5 tens and a 9. So this means 59 60s and a 1. So what is that? 59 times 60. Anybody have a calculator? Let's not take the time to do this by hand. It's easy to work out. It's 3540. This is 3540 and one more, so 3541. Okay? That's what this number represents in this column, 3541. Okay? Column 2, what's this number? Line 7, column 2. What do we see here? I see 3 tens, 1, 2, 3, and 8 instead of 9. Do you see that? 1, 2, 3, 4, 5, 6, 7, 8, but no 9. Ah, thank you. How do I do this? I guess I can do that. Do you see the 3 tens? Do you see that there's no 9 like there is there? There's 8 but not 9. So I count that as 38. And what's next to it? A 10 and a 1. A 10 and a 1. Does everybody see that 10 and a 1? So that makes 11. So what is this number? 38 times 60 plus 11. 38 times 60 plus 11. Let's do it on the calculator. 38 times 60 is 2280 plus 11, 2291. So they saw this. People kind of people understood that this should be some kind of tabulating something. What the hell are they tabulating? 35 41 squared. 35 41 squared, let's do it on the calculator. 35 31 squared. 12,538,681. How about 2291 squared? 2291 squared is 5,248,681. And the difference of the two is 7,290,000. Which is 2,700 squared. So what's on this? What's all over this tablet? Pythagorean triples. Pythagorean triples, about 1,000, 1,500 years before Pythagoras. Okay? Homework, since we're running out of time, exercise 2. Exercise 2, work out line 8. So that was line 7. Line 8 is the next one. Don't work out line 9, because line 9 has a mistake in it. Apparently this was a student's homework assignment in ancient Babylonian. And this was the homework that they handed in to their teacher to be corrected. That's what it seems. And in fact, the word at the top here, this word is diagonal, and this word is width. That's the translation. And then this first column, I should say, column 1, by the way, column 1 is a ratio. So if I call this number d squared, the diagonal squared, and I call this number width squared, then this they called length squared, and the column is diagonal squared over length squared, expanded out in sexagesimal. So if you look here at the beginning of column 1, there's a leading 1 that you can't see. I'll try to do it side by side. There's a leading 1, and then what is that? Looks like 43. I mean, you have to stare at it. It helps to have the original. By the way, the original is sitting in New York City at Columbia University. You just show up at the library there. I mean, you have to Google exactly where to go. You say, "I'd like to see Plimpton 32, please, 322," and they just bring it out to you. And they have a replica that you can hold and touch and see what instrument it is that makes these. There's one side that makes the 1s, and then you flip it to the other side, you make 10s, and that's how they would punch these things into clay, and the clay survives 4,000 years. There's a 43, so that's 4 and 3, and the next thing is, just so you know, an 11. That's right, that looks like an 11. You see that 10 and that 1? Everybody see where I'm pointing to? And the next thing is a 56. And you see that? It's hard to see. That's a 5, and this is a 6, and then more. 56, and then there's some more things. And if you work out what 1 plus 43 sixtieths plus 11 60 squared plus 56 sixtieths cubed is, you'll get in decimal about 1.71998. And if you work out what 12,538,681, which was d squared, can you still see where d squared is? Yes? Divided by 729,000, you also get 17,1998. Okay, so part of the homework was to work out d squared over L squared, and that's column 1 to like 5 sexagesimal places. 4,000 years ago. All right, next time we will complete the proof of this theorem, which was known 4,000 years ago in ancient Babylon, and prove Fermat's last theorem for the exponent form. This is all to motivate why we want to study quadratic forms. Higher degree equations, there's a lot of beautiful things to study, but usually the solutions are in the negative. We want there to be not solutions, or very few solutions. Quadratic equations, there's lots of solutions, and there's a big, beautiful, flourishing theory involving geometry, representation theory, and so on.